Hello, and thank you for watching this presentation on the Internet of Things. I'll be talking about IoT and trends and implications for enterprise and data science. I'm a principal data scientist at Pivotal. My name is Rashmi Raghu, and we at Pivotal have a strong global data science practice. We're about a team of 30 or so people, and we engage in data science projects for customers and clients all over the world in various flavors, and IoT is a big part of that. Let me start actually by asking a question. What is it that we think of when we hear the phrase Internet of Things? It's become really big these days. What can the Internet of Things do in the real world? For instance, how can we use it to prevent accidents like the 2010 Macondo disaster? Or if you're in retail, financial services, telecommunications, and so on, how do we know when a customer becomes likely to default on a loan or churn, these are very important aspects of the business. How about looking at the utility space, the electricity transmission grid? How do we know, for instance, when a tree has fallen on a power line or other issues such as power theft, even before residents start to complain? These are all key questions that I think the Internet of Things is in a great space to be able to answer. Internet IoT, the mashing of big data with big machines and its usability and investability has become there's a lot of excitement and a buzz around this area. And this is where data science also comes into play. It's not just storing of data, but also what do we do with the data once it is stored? How can we use data to help us answer the questions that we're seeking to answer? That's where creating a smart system comes in. It's not enough to just collect and store the data. It's not enough to simply look at what happened historically and inform and just cognitively inform ourselves about what to do. We're now in the space where we're capable of building predictive models within a smart system which can help us make decisions that we can execute upon to gain competitive advantage, to make a business successful, to help people eventually. In this context of a smart system, let's think about the analogy of a human being. How does a human being react to an external event? What is it that we do that's so special? Well, the human being has a brain which brings it all together. Be it sports or be any other activity, we human beings are able to take input from our senses, such as our eyes and ears, and our brain analyzes it to compute, say, in the case of baseball, the trajectory of the ball, and tells the body what action to take to hit the ball. Similarly, the idea is, analogously, we need to make sure that the organization can do the same thing. Sensors are now becoming ubiquitous all over the place. There are also capabilities of acting on this information. But where is the brain, right? Where is the organizational intelligence? There are, as I mentioned, lots of sensors around. There are things we can do to take action, say, in the case of machine failure, stop a machine from going too far along, making sure you shut down maybe the equipment before anything disastrous happens. How can we make sure that this connection between sensors and actions is both seamless, it's intelligent, it's smart, and not just relying on looking back, but also looking forward? That's where the concept of a digital brain comes in. The brain is what brings it all together, just like in a human being. So in the case of an organization, technologically speaking, we can take input from a large number of sensors, build a model to analyze the incoming data, and tell the actuators or even the people taking the action help people along regarding what action to take. And this is typically distributed over a network of machines. Sensors are all over the place. Mobile devices are individual points. And so even the data that's collected is so large that it doesn't necessarily fit on a single machine and has to be distributed across and worked on in in a distributed fashion. And we're here at Pivotal to help enterprises to become data-driven. So we're helping people along the journey to becoming a data-driven enterprise. In many cases, the data infrastructure itself has to be modernized in order to collect and keep a lot of the data that's being generated, rather than saying there's not enough space or the velocity at which the data is coming in is too high to be able to store, so a lot of the data might get thrown out with legacy infrastructure. Modernizing the data infrastructure. We see this as a virtual cycle, actually. With the data, we can perform advanced analytics, discover insights, and it's not just enough to stay there. One of my colleagues has a nice way of putting it. She says, PowerPoint is sometimes where our models go to die, and that's what we want to avoid. We want to be able to leverage the analytics and the insights generated from all of this data stored and deploy them in analytic apps, automated at scale, so that decisions and responses to events can be done at scale and in a data-driven manner. Smart systems, creating a smart system, therefore, involves sensors, the digital brain that we just talked about, and actuators. And part of the digital brain, of course, is data science. Data science hinges a lot on these 4 steps that is listed here, and I'll talk a little bit more about that in a few minutes. First step, of course, the key part is formulating the right problem with the customers and clients at the table. It's not that everything is right now end-to-end solutions, black box. That's not something that is currently advocated. That we definitely have to sit down with our subject matter and clients in order to formulate the right problem and take the data at hand, see if there's enough there to address the problem, break it down into steps, and iterate along this process of working with the data with the right feature, building the right features, choosing the right model, and then deploying it in an application step. Of course, all of this hinges on on using a big data platform, a platform which enables this iterative cycle to happen at scale and in a very agile and fast manner. Pivotal's Big Data Suite offers this type of platform with Hadoop, Spark, Pivotal Greenplum database, Hawk, which is our SQL and Hadoop engine, as well as Cloud Foundry, which enables all of these apps at scale. And all of this, of course, talks back and forth to sensors and actuators. That's how we can derive the advantage of a smart system. And I'll go very briefly into what we mean by what I mean by the Pivotal Big Data Suite. Just a brief introduction. A lot of my other colleagues at EMC World are talking about it already. So this will be a quick slide. Our Big Data Suite, of course, consisting of all the data products that you saw before, is the first open-source enterprise class data portfolio. We are able to execute analytics at scale and in an agile manner on that. And it is, of course, cloud ready as well. And with platforms like this, we can help take our customers on the Internet of Things journey. Everything from storing, just plain storing the structured and unstructured data coming in at high velocity as well, all the way to innovating at the other end, with agile app development, with deployments at scale. Primarily, along the way, of course, I'm primarily talking about referencing data-driven apps, where the data behind the data that drives the intelligence behind the apps is really of very large scale and of great complexity as well. So I've talked a lot about what it means, the notion of a data-driven app, and the intelligence and the data science behind it. What do we know when I say data science for IoT or data science in general? It was a few years ago, it was not a very well-known term, but now the use of that term is quite ubiquitous in the big data era. So what does data science mean to you? When you think about data science, all of these words might come in, might pop into your mind. Machine learning, MapReduce, big data, business intelligence, time series, visualization, distributed computing, decision science, and so on and so on. At any given time in any given project, we might be using any or all of or many of these topics or skills, if you will. Just to level set, this at Pivotal Data Science, we think of data science in this quite comprehensive fashion. Putting this up here just to level set what we mean by data science. Data science is really for us the use of these sophisticated analytical techniques, machine learning and beyond from various domains on various different types of data to extract many insights from many types of insights that eventually drive automated low latency actions in response to events of interest. That's really how we approach data science. And specifically, I mentioned to you the iterative approach of data science, and we have one of my colleagues, Kaushik Das, has got a good blog on this subject, where we consider a cycle of 4 phases in our data science engagements, along with 4 differentiating factors that you see alongside the 4 phases. The key, of course, is to start with a problem formulation and then iterate on that. Once we formulate the problem, we need to do so, or when we are trying to formulate the problem, we need to do so in a way that is relevant to the goals and pain points of the stakeholders. And once we have a problem statement to start with, we can go into the data step to build the right feature set, making full use of the wide variety of data, the volume of data that's available, and then choose the right model that goes from answering just what, where, and when to why and what if. Eventually, of course, packaging all of this in a framework or a way, whether it's dashboards or apps, to help the decision-making processes and help people take action on the data generated by the Internet of Things. Along the way, of course, we need to be mindful of selecting the right technology for the problem, using an iterative approach, which is, of course, why we have this cycle here. It's not just a linear waterfall type approach. And being creative at every step and building the right narrative, not just for a narrow team that might have approached us for a project, but also the broader set of stakeholders that would be available or benefiting from the project. Of course, the Internet of Things means that there's the range of different verticals, the range of different data sources, the range of different problems encountered in IoT is very broad. We have lots of mobile sensors, lots of medical image data. Video surveillance is huge. A lot of video surveillance is just manually looking at things, but of course, there's a huge potential for data science there. Oil and gas exploration, and I'll talk about some work we did in this space. Of course, there's social media, stock market, generates a lot of gene sequencing, smart grids, and so much more. There's billions and billions of data points here, and we need the right sort of platform in order to address or use them. I touched a little bit on Pivotal's platform. Some of the other things that you see up here are the data science tools, languages, and methodologies that are very popular, R and Python. Of course, MATLAB is our in-database analytics suite. It's essentially machine learning that you can do on SQL, and it's open source. Many of these tools and languages, I'm sure, are familiar to all of you. Ultimately, of course, we are trying to apply many of the techniques, such as to problems that involve these types of topics, right? Clustering to identify unknown patterns, classification to say whether or not say a machine is going to fail in the next certain amount of time, to optimization for optimizing decisions, regression and forecasting, and so on. So this is sort of an overview of what we think about data science, how we approach it and how we apply it, where we apply it essentially. So let me go a little bit into what this means for IoT, what we're seeing with our customers, what we're seeing in the industry with regards to trends and implications. And here the trends and implications are, I'm going to talk more about more from the perspective of what are the verticals involved and what are the common themes that we're seeing in these verticals and how one might approach them. At the end, I'll give a couple of use case examples. So IoT, as I mentioned, is ubiquitous. Sensors are instrumenting many, many things now in the energy sector, transportation, healthcare, lifestyle, financial services, even retail, communications, even agriculture and farming, which might not have occurred to some folks. With the advent of the industrial internet, of course, we are now also seeing this concepts of smart cities, smart homes, connected cars, coming through, connected wearable devices and so on. In fact, there are a couple of sessions here at Pivotal, one on connected car, other than my own, one on connected car as well, and then another on enabling IoT, which I will point to at the end of my talk. In each of these verticals, of course, we have several themes or several types of use cases emerging. There are common types of use cases across these verticals. Predictive maintenance being the canonical one that we're seeing in many of these verticals, not just one or two. Then there's the increasing need for security analytics, because malware is now no longer just limited to your PC or your laptop. It's now spreading into all of these devices that are instrumenting, whether it's cars or whether it's a production line. Then there's the question of predicting the quality of products and systems, anomaly detection, whether it's smart grid or any other system, recommendation systems not just for movies or products, consumer products anymore, and I'll talk a little bit about that, as well as demand modeling. To go a fraction deeper into this, this is not meant to be an exhaustive list of use cases, of course. A couple of key examples from different verticals under each of these topics is what I'm mentioning here. Under predictive maintenance, something I will talk about in the energy sector, are predicting drilling equipment function and failure, something we have done, a project we've done in the past. This is useful for optimizing drilling efficiency and maintenance schedules. Manufacturing, in the manufacturing space, for instance, take the example of predicting failure of disk drives in servers to help in planning replacement schedules. Security analytics, healthcare devices and smart grids as well are in need of detection of malware, network intrusion detection, of covert threats in all of these devices. Again, in the space of predicting quality of the product or the system, think about predicting the output of a manufacturing process. In this case, we've done a project on predicting vaccine potency based on manufacturing sensor data. And in the space of transportation, one example is predicting the duration of road traffic incidents, something we actually have an active demo on, which helps improve the quality of one's commute and also is part of the smart cities concept, if you will. On the other side, if we look at demand modeling, recommendation systems, and anomaly detection, demand, of course, we can have enhanced in the retail space. We can have enhanced and granular modeling of consumer demand using large historical data repositories and point of sale records. And the other typical canonical use case in energy, especially in the smart, given the smart grid, is an improved ability to model electricity demand, which is quite crucial. I'll touch upon recommendation systems, which I said isn't just for movies or consumer products anymore. Consumer products is typical to think about, but think about the manufacturing space where after the product has been sold, you have post-sale maintenance that needs to be done. And in this case, one can think about recommending parts and service methodologies for this kind of maintenance. Another, last but not least, anomaly detection is a key component or a key topic. Think about needing to figure out if there's been a vegetation issue, like a tree is obstructing a power line, and causing an anomaly, or there's power theft, which is an anomalous usage, anomalous behavior in the network as well. In the space of manufacturing, it may not always be easy to know whether the product that's coming out is of good quality or not. Sometimes that involves a lot of detailed analytics there as well in the form of anomaly detection. In this example, I'm saying identifying die failures, anomalies from wafer bin map images. So I'm getting a couple of specific examples here so that you can see the flavor of the types of use cases across different verticals that fall into some of the same buckets. Given all of these common use cases, we also have a lot of general and common challenges in IoT use cases. For each vertical, these may look different because the data would be different. But think about all of these different types of challenges that we have. On this side, you see the challenges I've listed have to do with the data themselves. And on the other side, while the challenge also has to do with the data, it's a little more nuanced than that. Some of it has to do with the modeling as well, what you do with the data. And we have to address all of these challenges in any project to create value and to understand the value of this. Value creation from a lot of IoT data is still in its infancy, where some verticals have moved further ahead, some verticals are still grappling with how to store and look at the data. But in any case, value creation requires that we deal with a lot of these challenges. And we have to see this as an opportunity. It's not that we look at these challenges and stop there. There's a lot of ways to deal with these, and I'll hint at a few in the next couple of slides. Think about the data location. Let's start with data location. The data from things and business processes are, different data sets and are usually on different platforms, different and not necessarily the interchange formats might not be clear. There may not be the ability to very easily join these data sources. But at least locating the data centrally in a data lake alleviates some of these initial access issues. There is no data science without data. Therefore, the first step is to at least alleviate some of these access issues. No data, of course, is clean. There's no such thing as completely clean data. So data cleansing is always a step that we data scientists have to go through. There's missing values, dirty data in the presence of sensor or device malfunctions. And we can actually implement some intelligent analytical techniques to resolve these, because when data is being stored at scale, it's no longer possible for you or I to simply sit and parse through the data and say, okay, here are the things that we'll keep, and here's how we'll correct some of these challenges. We have to use some intelligent techniques, data science techniques, to help resolve these issues. Same goes for data integration. Integration of IoT data with business data and external data can be non-trivial, even data from different IoT devices. Right, different types of devices. Tools from statistics and machine learning can actually play an important role here too. So, we can have algorithms that recommend natural join mechanisms for different data sources and so forth. On the other hand, when we talk about this challenge of normal versus anomaly, the ubiquity of IoT and the types of data that are being collected, new types of data are being collected. The instrumentation allows for that. And they might be poorly understood. What does it mean when the value is X or Y and what have you? In this space, unsupervised learning techniques can help uncover normal and anomalous patterns to begin with. So that's what I mean by the challenge of knowing what is a normal pattern, what's an anomalous pattern. If you think about the example of the smart grid, different people in different businesses use energy in different ways, and that's normal for them. But just because you see something different doesn't mean it's an anomaly. It's necessarily a bad thing. What do I mean when I say labels, labels, labels? Label data, much like not knowing what normal and anomaly is, labeled data for training models is hard to find. What is labeled data and what is training a model? If you're trying to predict, say electricity demand or customer demand, knowing the previous history of demand is important. If you're trying to predict whether a machine is going to fail or not, knowing when failures occurred in the past is also important. But that may not necessarily be clearly indicated in the data. And I'll talk about some of those challenges in a little bit. when I talk about the use cases, that is, these problems we could approach in 2 stages. We could use unsupervised learning techniques to create, to learn about what the data is showing us without necessarily needing prior labels, and then either instrument them to capture the right kind of data labels, or even use these different buckets to build supervised learning and regression type models within these buckets. And last but not least, we need to be cognizant of how tolerant a user or a business is to false alarms. That's false positives. Say you're mentioning that something might go wrong, you're predicting something might go wrong, but in fact there's nothing wrong at all. No model is perfect, so there is always some element of false alarms, and no alarms, actually, false negatives. So how tolerant is a user to false alarms or no alarm when there should be one needs to be taken into account when the model is being built and tuned. Some techniques that can help alleviate some of these issues are, using ensemble models to improve the predictive power of models and reduce some issues. That's sort of a generic way of thinking about this, but in the end, it really does come down to knowing what the business problem or the user at hand is comfortable with in the realm of false positives or false negatives. So given all of these challenges, there are lots of ways to address them, and as IoT space matures in different verticals, there will be some typical ways to address many of these challenges. In terms of data location, as I mentioned, starting with the data lake concept is actually a very useful thing. So let me actually now move on to giving you a flavor of the kind of use cases we've dealt with in the IoT space. I'll start with, I'll go through hopefully 2 use cases, and I'll start with the use case about predictive analytics for drilling operations in the oil and gas space. We've all, I think, heard the phrase data is the new oil, referring to data as the driving force for the economy nowadays. And it's very apt, really, when it comes to the oil and gas industry. I'm going to talk a little bit about how we can use the data, especially from the drilling space, to produce, to help the oil and gas industry produce value from that. Oil and gas exploration and production activities actually generate a lot of data, large amounts of data from sensors, logistics, business operations, and more. And the rise of the cost-effective data collection mechanisms, storage, and computing devices is really giving this space a big boost. But the promise of data as the new oil can really be realized when we can tap into its value in a meaningful and cross-functional way to enhance decision-making, which really is what provides the competitive advantage. So let's look at this concept for the predictive maintenance space, especially predicting drilling equipment function and failure. The idea is to take steps towards zero unplanned downtime. The downtime when we're trying to drill is whether due to equipment failure and other things is actually quite expensive. Drilling wells in general, of course, is an expensive process, and any equipment failure or any downtime is damaging. The drilling motor failure could account for hundreds of thousands of dollars in damage, and given that there were hundreds of thousands of oil and natural gas wells in the U.S. and many more now, I suppose, these problems could result in costs in the order of billions of dollars, right? And the goals of predictive analytics for drilling, with drilling equipment function and failure prediction, is to try and provide an early warning system, which is something that most folks don't have at the moment. Trying to predict what the remaining useful life of equipment might be, what the probability of failure in the next future time frame might be, and so on. Along with that, it's also to provide insights into prominent features impacting operation and failure, so that if there are certain things that stand out as causes of failure or highly correlated with failure, then those can be addressed. With eventually, hopefully, reducing non-productive drill time, which reduces costs, and reduction of failure incidents themselves, which, all of this improves health and safety, improves environmental risks, and of course can greatly reduce costs associated with drilling, and therefore make things more efficient and provide a competitive advantage. So let's dive a little bit deeper into the problem itself. This particular use case I'm talking about, we've done a couple of different things in this space. So this set of slides is sort of an overview of those projects. Usually in the beginning it starts off, of course, with data integration and cleansing, building the right features and modeling. And there's, of course, this is a loop. It's not so much linear like this. The primary data sources for addressing predictive analytics for drilling operations are drill rig sensor data, measuring things like rate of penetration, RPM, torque, and drill operator data, which contains things like drill bit detail, failure details, component details, and even notes and comments. The sensor data is really time series data, often thousands of data points per hour, and could run into, depending on the number of wells and the number of days or weeks of data that there is, or months, might run into billions of records or more. Operator data, which might be more manually entered, typically is much smaller in scale, but despite the scale differences, they need to be integrated together in order to derive the best value from them. And operator data, in this case, of course, when we were looking at equipment failure, it wasn't that the data contained clear indications of, hey, is this failure true and false? It was the fact that the operators would have maybe some of this data would be in the form of comments that the operator wrote down. Hey, this failed, or that event happened, etc. Event X happened, and they may not even use the words failure, etc. in the comments, which means there is a pre-step of teasing out the failures and exactly when they occurred by using natural language processing techniques on the data. In terms of actually performing these projects, we need to be able to use the right technology. It needs to be able to handle all the phases of the analytics cycle, to be able to handle the scale of the data and the analytical models themselves, support the development of complex predictive models, provide the ability to build a framework for integrating different types of data, including structured and unstructured data, ability to analyze both of those. Essentially to support fast computation of hundreds of features on time windows with hundreds of millions or billions and trillions of records of time series data, and as well as in this case we needed the ability to use a natural language processing pipeline for analysis of operator comments to identify failures from unstructured text. And so these are some of the examples of the platform and tools that we used in these projects. We built out, based on using these platforms, a comprehensive framework for data integration, including processes for cleansing the data to impute maybe missing values or manually entered operator data cleansing, which is often prone to errors. There are also invalid values in sensor measurements. In some cases, you may choose, depending on the problem at hand, you may choose to ignore the nulls and outliers if they're few and far between, and ignore some of the missing values, but in many cases you may need to use more sophisticated techniques to address the fact of imputing them. Aside from that, integrating operator and drill rig sensor data also means that you need to be able to standardize the columns that are used to join across these different data sets. In many cases that may not be true. For instance, take customer data. If in one data set you have a column where your name is in the order of first name and last name, but maybe in another data set which you need to join to the first one, your name is in the form of last name, comma, first name. That is fundamentally a formatting issue, and that those kinds of issues, and maybe there are inconsistencies in the same column containing the names, and those kinds of inconsistencies need to be addressed, sometimes in very sophisticated ways. In the case of the drill rig example, well names across different data sources might have different formats, and that means they need to be addressed either through very simple regular expression transformations or more sophisticated fuzzy matching techniques and other data science and statistical techniques to be even able to join these data sources at scale. The idea at least is to be able to do this maybe even in an automated fashion, maybe 80% of the way, and only the last mile is something which the human needs to pay attention to. Given that the data is integrated now, sometimes, in many cases, it's useful to generate features, not just use the raw data as itself. Depending on the problem at hand, the features that are generated can make a big impact on the predictive power of the model, how good the model is. And we can generate a complex feature set, especially in this time series data with the drill rig sensor data, based on the data coming from the sensors. And we can leverage things like Pivotal's data products and MATLAB and PLR and PL/Python, which are heavily utilized as well for fast computation of hundreds of features over time windows. Think about features like moving averages or moving distributions over windows of time series data. It isn't enough to capture then just one data point per time window. You really need the time resolution of all of the sensor data in order to make meaningful features out of it, even if the features are being done in a semi sort of aggregated manner. There are some nice blogs on how to handle time series data on the Pivotal website if you're interested as well. Now, what can we do with all of this data and the features? There are different questions we can ask even in the space of predicting drilling equipment function and failure. Think about predicting rate of penetration, predicting remaining life of equipment, predicting the occurrence of equipment failure in a chosen future time window. And I'm just listing a few examples of machine learning algorithms you might be able to try. This slide doesn't mean that these algorithms are the ones you have to try or that these are the ones that work best. That's not the intent of the slide. It's an example to show these are models you can try along the way, and maybe something like linear regression might not really work very well for the question at hand. However, for other problems where it is useful, it needs to be done at scale, and the point is that all of these are examples of machine learning algorithms that need to be used, that we need to use at scale, and things like MATLAB and now Spark and MLlib these algorithms need to be built out and used on those platforms. Just a quick note about MATLAB. The website is matlab.net. This is just a flavor of all the algorithms that are available in it. It's basically big data machine learning in SQL. Using a SQL interface, you can run these algorithms at scale, and you can also run these algorithms at scale. And there's many more coming along the way. It is also an open source product. And coming up, of course, we are also paying a lot of attention to Spark and the growth of MLlib on Spark as well. What does all this mean for the drilling problem? What have we talked about so far? The whole point was to get us one step or many steps closer to zero unplanned downtime. Every incident identified prior to failure potentially saves hundreds of thousands of dollars. There is now a growing ability to fully utilize big data. We can build out with these platforms comprehensive data integration framework, platform and techniques. And along the way, for our customers, we also tend to try and give feedback on what sort of data capture techniques and data curation techniques might work best to address some of these problems. Like, for instance, capturing the incident of failures much more clearly and avoiding the vagueness of maybe some of the comments that might be typed in, instrumenting for those kinds of things, as well as providing them feedback on what sort of platforms and tool sets and algorithms might be best to address the problems that they're most interested in addressing. We showcase the ability to build and operationalize complex and extensible predictive models, all with the goal of going towards zero unplanned downtime, improving efficiency, reducing costs and risks both health and safety and environmental. So that's from the oil and gas use case space. Now let me talk about another vertical, the idea of helping reliability engineering in the IT infrastructure. Typically you think about IT infrastructure as being, as being sort of complex. There are different technology components with lots of dependency. But the role of reliability engineering is really growing with the expansion of these networks and the need, and so many of the online companies and so on. The need to ensure 24/7 uptime is great. The need for network monitoring and quick resolution of incidents is really great. All of these devices, all of these machines that are deployed in an IT network may generate alerts at high volume, and in this particular case we worked with a financial services company where primarily dealing with alerts and incidents was an eyes-on-glass operation, people looking at the alerts coming in and then figuring out if there's some important trend happening in the short term or not. The types of data we had to use were, event logs, performance logs, incident tickets, and so on. What intelligence can we mine from this data to improve the operational efficiency of reliability engineering? That is, try and do 80% of the work so that when people look at it, they can respond to it in a more meaningful way. In the particular case of this client, they had multiple business services from which data was coming in. For the purpose of this project, we only had a small slice of data from one business service and from multiple devices. They had a rules-based engine that was managing the alerts. There was some manually created incident tickets, and then it was moving on to incident resolution. The alerts coming in are actually semi-structured text. So imagine a device, a machine saying say going towards disk full or an error because the disk was full. And then there are network-based incidents, there are incidents which are unstructured. Alerts, as I mentioned, are semi-structured, and there's incident work info as well, how incidents might have been resolved. The opportunities to do data science in this reliability engineering space are actually quite important and quite high. Think about the questions of what are the typical failure patterns? How could we identify that? How might that help us in future? Maybe there are some really typical failure patterns that are causing a lot of the events, but that have a very simple fix. And then that will reduce both the volume and maybe the velocity of the alerts coming in. On the other hand, given an incident and historical resolution data of some serious incidents, can we recommend a set of resolutions? This again goes back to the recommendation systems a point that I made a little bit earlier. And then, of course, just like the oil and gas space, can we predict failures before they even occur? Let's just look at the first question for now. For this project, we actually had just a small sliver of data, about 10 million alerts from 6 months of data from just one business service. And of course, there's lots of business services and lots more data to be had. The data is multi-structured, semi-structured, non-structured data. There's no labels to the data. There's no indication of what is a serious alert and what is not. These alerts and incidents are textual. They have short text, and we really need to use clustering techniques at scale. And cluster interpretability for further evaluation is, in fact, a challenge as well. Here's a little workflow that is part of this process. When alerts are coming in, they're short sentences of text, and they often contain specific dates, times, and IP addresses when they occurred. Such details are actually not important for figuring out what type of alert it is. Of course, when you're trying to predict failure, that's a different matter. This type of data is important for that use case. However, when you're trying to figure out which bucket or which type of alert this is, then it's not that useful to have that complicating information in there. There are also the words that are common in the English language or other languages, to, the, and so on, which may not be that important and could be removed from the alerts without jeopardizing the quality of the clusters that come out of it. Once you have those typical steps done, it's necessary to be able to choose a type of comparison metric to compare different alerts together. Ultimately, if you want to know if one alert is similar to another and you're expecting a machine to do that, there needs to be a mathematical representation of a distance or some sort of similarity metric between alerts. Once we generate that kind of distance from pairs of alerts, we can use many different techniques, whether it's hierarchical clustering or graph theory based connected components approach to identify clusters and then present them as visualizations. I'll show you a couple of visualizations in the next few slides that will help elucidate the meaning of these clusters. So each node in this particular graph is actually an alert, and you can see several of these are clustered together. But what does each cluster actually mean? Here I'm showing a visualization of different alert groups within which there are individual clusters. The size of the bubble represents the size of the cluster. And one interesting thing you can do with some of these cluster results is figure out what the distribution of resolution time is for some of the incidents. Not every alert is an incident. Some of these alerts are just alerts. But if there were serious incidents, what was the mean time to resolve these incidents? What was the time, what was the distribution of this time across the different clusters? And that's quite important to know. If there is a small cluster, but it's taking it contains incidents that were so serious it's taking a long time to resolve them, then one might choose to take a certain type of action on those. Aside from that, just trying to figure out what types of alerts were in each cluster, what the theme of each cluster is, requires more thought into visualization than just presenting word clouds. If you think about text data, you might think about word clouds. But imagine in this case we have 3 different clusters, and everything to the right here that is highlighted represents some of the keywords in the order in which they appear in the alert. For instance, the last one on at the end there refers to a hardware error. The first one is about an exception encountered, a core dump exception. And the middle one is basically an alert saying it indicates a harmless alert, as the words indicate. So we need some novel cluster visualization techniques in understanding what's coming out of these techniques. To look at how one might operationalize this, look at clustering on, say, a 3 to 6 month time window of data, assign incoming alerts to existing clusters according to the distance criteria that we've defined, and we can monitor cluster statistics such as the time to resolve, number of incidents, and so on in an app or a dashboard, and perform clustering again every few months or however frequently is needed for the particular business problem at hand. And we may discover, of course, there may be emerging patterns and new clusters that come out of this. So that's why you need to continue the process, and it's not a static thing where you've got a black box model that's deployed and we're done. These models we need a frame. We try to incorporate a framework in which you can reuse and update some of these things. So these were the products that were used in this use case. As you can see, it was primarily based on the Greenfield database with MATLAB, R, Python, and a bunch of different visualization techniques. The key takeaways and lessons learned is we've helped understand where your alerts and incidents are coming from, and that's an important step in improving infrastructure support. It helps in profiling classes of alerts. It'll help eventually in resolution recommendation, in an application for hardware failure prediction eventually, and reduction in time to resolve some of these serious things. We've used a distributed computing architecture and proper algorithm choice, and these are needed to deal with the scalability issues because the volume of the size of the IT infrastructure and the volume of incidents and alerts generated are quite big. And in order to understand some of the results that are coming out, we also need intelligent dashboards and visualization techniques. with that, I'll just end on this, on a couple of last slides, taking you back to the verticals that I described that are common, and that IoT is really impacting in a very huge manner. And Pivotal Data Science team, our team, has is in the business of generating value for all of these verticals. We've executed projects in many, if not all of these. And I encourage you to check out our blogs. Pivotal has, for further info, you can check out the general Pivotal blog, and there's a data science specific section to the blog as well. You can get more details about the big data products on the Pivotal Big Data website. And specifically, the oil and gas use case and IT operations use case webinars are online. I've got videos and slides, and the IT operations one was also presented as a paper at KDD last year. And I'll just end with pointing you to the list, a website with the list of Pivotal sessions at EMC World. And in particular, 2 of those sessions are about IoT. The first one is a connected car demo happening later on Monday afternoon, and the talk on enabling the Internet of Things is also happening on Wednesday. And with that, thank you very much.